a couple of videos for this one on projectile motion. So our objectives for today's video are for a projectile to describe the changes in the horizontal and vertical components of its velocity when air resistance is negligible, and to explain why a projectile moves equal distances horizontally in equal time intervals when air resistance is negligible. So from section 3.4 in your books, projectile motion, some examples of projectiles are a cannonball shot from a cannon, a stone thrown into the air, from a slingshot perhaps, a ball rolling off the edge of a table, or a spacecraft circling Earth. And you can see there I have a soccer player kicking a ball. That would also be a projectile. It is not a ball rolling down a hill because the projectile must be in the air. It must have a free fall component. Now, when a projectile is in the air, the type of motion that best describes the horizontal component of motion for a projectile is a ball rolling on a level surface with no friction. And we talked about that last chapter. We had in our CDPP, we had a ball rolling across a floor, and we saw that the velocity remained constant across the floor with no friction. The type of motion that best describes the vertical component of motion for a projectile is a freely falling object. So those were our other pictures where we had the object just being dropped or it being thrown straight up and coming straight down. Now, a couple of important things to know. The horizontal component of a projectile's velocity is independent of the vertical component of its velocity. We can take them apart. This is the whole reason for doing the vector resolution right now, so that we can take that motion that seems to be going slanted and we can break it into its x and y components. The vertical component accelerates in the absence of air resistance. So the vertical component is like our free fall problems, where there is acceleration. And the vertical component varies with time in the absence of air resistance because of our equation. Distance equals 1/2 g times time squared, so that varies. Where the horizontal component, the velocity is constant the whole time. So taking a look in section 3.5 at some upwardly launched projectiles, I want to refer to figure 311 and 312 on page 36 of your textbook for this part. So we're taking a look at figure 311 in your book, and there are some things that we want to notice in this picture. The first is that we have taken the path and we have broken it and we have resolved the vectors. We have broken it down into its x and y components here for the purpose to show you that the horizontal component of a projectile's velocity is independent of the vertical component of its velocity. Remember, we said at the beginning we can take a look at these as if they're really two separate problems. One involving gravity and the vertical, and the horizontal like it's rolling across a table. One free fall, one rolling across a table. So some things we notice are this horizontal component. Notice it's the same length in each spot. That's because the velocity remains constant in the absence of air resistance and or friction. So it is remaining constant. What we notice here is the vertical component changes. This is because it's like our free fall problems. As it goes up, the velocity decreases. At the top, there is absolutely no vertical component. All velocity is due to the horizontal component. Now, this is different from our free fall problems because it doesn't stop at the top like it does in free fall when we throw a ball straight up and straight down, because there is this vertical component to the velocity. It is still moving at the top of its path. And then here we add in that velocity, the vertical velocity component, and we can see that it accelerates on its way down because it's getting larger, where the other one is not accelerating. It's at constant velocity in the horizontal direction, not the vertical direction. We also see that the resultant, its actual speed, is more than either the vertical or the horizontal because of the fact that when we resolve these, the hypotenuse of a right triangle is larger than either of its sides. So we're combining a lot of things here. And if we take a look at figure 312 as well, same thing as the other figure, except for this is a little bit steeper. We can see again, these horizontal components are all the same length because it's at a constant velocity in the horizontal direction, but acceleration is changing. Velocity, or acceleration is the same, excuse me. It has constant acceleration of g, but the velocity is changing as it goes up and down in the same manner as figure 311. To wrap up that section, what we just talked about with those pictures, some important points are at the very top of the projectile's path, its velocity is entirely horizontal. That vertical component is gone because just like in free fall, when it gets to the top, it stopped for a split second. Well, so there's no vertical velocity, but there's still horizontal velocity. And looking at the resultants, the minimum speed is at the top of the projectile's path because all of the velocity is the horizontal component. There's no vertical component to add to that like there are for when it is going up and when it is going down. Now we're going to take a look at figure 3.13 on page 36 of your textbook. In figure 313, we have a soccer player kicking the ball at different angles. And what we see is the distance it travels when that player kicks it at different angles. And the important thing to see here is that at a 45-degree angle, the ball will go the farthest. At that 45-degree angle. And we can also see at 15 and 75, it's the same because 75 minus, or 90 minus 75 is 15, and the same with 30 and 60, it goes the same distance because 90 minus 60 is also 30 as far as our triangles are concerned. For a right triangle, it would be basically equivalent. So the best angle to kick a soccer ball to get it to go the farthest is a 45-degree angle. So remember that, you soccer players. The big takeaway from this figure is that in the absence of air resistance, a thrown ball will travel the greatest distance across the ground if it is thrown at a 45-degree angle. So remember this, you athletes. If you want it to go the farthest, throw it at a 45-degree angle, or if you're a soccer player, kick the ball at a 45-degree angle, or even in a kickball game. So use physics. You can use physics to help you with your sports. That's why it's important that we understand physics and we have an understanding so we can use it in these real-life situations. So our objectives for today were for a projectile to describe the changes in the horizontal and vertical components of its velocity when air resistance is negligible. So the horizontal did not change. The vertical does change because it's affected by gravity. It's accelerating. And explain why a projectile moves equal distances horizontally in equal time intervals when air resistance is negligible. That's because it is not accelerating. It is going at a constant velocity.